Let's take some time now to look at roots and rational exponents. So exponents and radicals undo each other. When we have the square root of 3 squared is written as the square root of 3 squared, the square root and the square simplify each other. This is because we can rewrite radicals using fractional exponents. The square root of x is equivalent to this x raised to the 1/2 power. And we see that when we take the same exponential expression and rewrite it using rational exponents rather than a radical, and we apply the power rule, we see how the 2 and the 1/2 cancel to just give us the 1. So our general rule is that when we are rewriting a radical expression or using rational exponents, the exponent is equivalent to the numerator of the fractional exponent, while the index is equivalent to the denominator of the rational exponent. And also as a side note, that exponent does not need to be on the inside. If I have the nth root of x raised to the m power, it is functionally equivalent. So any of our radicals we'll rewrite using rational exponents and vice versa, and simplify whenever we can. So our radicand is our base, and so then we look at our exponent, and that's the numerator, and our index is the denominator. Conversely, our base becomes our radicand, and our index is the denominator. Since it's a square root, we don't need to write it. We will, however, write 3. Now, the square root of 16 to the 3rd power is equivalent to the square root of 16 to the 3rd power. The second one is more preferable because I don't know how to cube 16 in my head, but I do know the square root of 16 quite easily as 4 to the 3rd power, and 4 to the 3rd power is an easier number to remember as being 64. When we have different bases with different exponents, there's a couple different ways we can write it. The first, while is faster, is least likely and least common, is where we write them both as separate radicals, the square root of x to the 3rd times the 3rd root of y. More commonly, what we're going to do is exploit the fact that we have fractional exponents and get a common denominator for those exponents. This allows us to write both bases as a radicand of one single radical. And so if we rewrite this as x to the 9/6 times y to the 2/6, now we have a common denominator with those equivalent fractions, so that we can now use 6 as our index and take the 6th root of x to the 9th power and y to the 2nd power. And we can break apart as well, and we can look and see, well, all of these exponents are going to have a common denominator of 4. So when I have a base of x, it'll be 6 to the 4th. The base of y will be 2 to the 4th. And the base of z will have 8 to the 4th. We can reduce each of those fractions, 3 over 2, 1/2, and 2. Now here what we'll do is we'll use the information that we have about our exponent rules and see what we can do to find out what n equals in terms of x. So we need to isolate n. So there's a couple ways we could look at this. We could say, all right, well, n to the negative 1/3 is the same as 1 over n to the 1/3. And we can rewrite that in radical notation as the cube root of n. And then we can get that out of our denominator by multiplying both sides so that we have 1 equals the cube root of n times x. And then divide both sides by x, we get 1 over x equals the cube root of n. And then to get rid of that cube root, we just cube both sides of our equation, giving us n equals 1 over x cubed. Okay, so that's one way that we can analyze it. But if we want to work it a little bit faster, what we can do instead is think about what property allows me to get rid of this exponent in one step, in one go. Well, in order to get rid of this exponent so that we have an exponent of 1, Well, we need to multiply this exponent by negative 3. I'm going to multiply it by its reciprocal. Well, the property that lets me multiply the exponent is the power rule. If we multiply both sides, or if we raise both sides to the power of negative 3, then what that allows me to do is cancel the exponent, leaving me with x to the 1. Then I have x to the negative 3, and just using my negative exponent rule, that becomes x 1 over x to the third. And so we end up getting the same solution that we had here in a much faster process. And last thing here is to know and understand that pretty much all the rules that apply to exponential expressions also apply to radicals, because we are looking at two sides of the same coin with fractional exponents. The thing we want to pay attention to when we're trying to multiply and divide radicals is the only thing that we have to know is that the indexes are the same. As long as the indexes are the same, we can either multiply or divide the radicands as necessary. So while I can't square root x to the third, nor can I square root x, because the indexes are the same, we can write this as the square root of x to the third times x. Then we can go ahead and actually multiply those together, and the square root of x to the fourth is something that we can simplify as x squared. Same thing with 3 and 27 as square roots. We can write it as 3 times 27 under the common radical, which gives me 81 and a square root of 9. Just like we brought these together to simplify, we can also split them apart, and we can identify that we have the cube root of 8 times the cube root of x to the third times the cube root of y to the sixth, and simplify each of those individually. 2x y squared. If we've got these fractions, we can also combine the fractions under one big radical and simplify the fraction within before applying the root operation. 8 over 4 simplifies to 2. X to the 8th divided by x squared is x to the 6th. Y to the 6th divided by y to the 6th simplifies to 1. And then we can look at just taking the cube root of the radicand we have left. The cube root of 2 times the cube root of x to the 6th. We can't simplify the cube root of 2, but x to the 6th can, as x squared. And then just to write it into a more reader-friendly notation, we put the x squared in front, and then cube root of 2.